In this chapter section, we will discuss Gibbs free energy, which is a thermodynamic function that help us to predict spontaneity of a process. You can read more detail of this chapter section in OER textbook chapter 17.3. In the previous section, we learned about how to predict spontaneity by looking at the change of the entropy of the universe, which come from the summation of the change of entropy of the surrounding plus the change of the entropy of the system. And the spontaneity of the process can be determined from both surrounding and the system. However, for Gibbs free energy, which is a thermodynamic function that helps us determine spontaneity of the process, we will focus on only the system. So in this case, we are not going to look at surrounding or the whole universe, but we are going to use only the system to help us predict spontaneity. The reason for that is because in chemistry, we are looking at, or our focus is the chemistry process or chemical process for the reaction. Therefore, we are going to put our attention into just the system or just the chemical reaction here to help us predict spontaneity of the process. The Gibbs free energy is derived from the second law of thermodynamics that I mentioned earlier. And we learned from the previous chapter that the change of entropy for the surrounding is equal to negative change of enthalpy of the system divided by temperature. So we can replace the change of entropy of the surrounding by this term. Then multiply this equation by negative temperature. So multiply this by negative T, this term by negative T, and this term by negative T. And you will get negative T times the change of entropy for the universe equal to enthalpy for the system, and plus negative temperature times change of entropy of the system. And you can rewrite this term to be a negative temperature times entropy change of the system, and you will get this equation right here. And we can define this negative T times the change of entropy of the universe as the change of the Gibbs free energy. So the change of the Gibbs free energy would belong to the system because enthalpy is of the system, and the entropy change is also of the system as well. And we'll get that the delta G of the system would equal to the change of enthalpy minus temperature times the change of entropy for the system. Therefore, this would be the new thermodynamic function that we will use as the system to help us predict spontaneity of the process, because delta G is related to the entropy change of the universe that can tell us about spontaneity of the process according to the second law of thermodynamics. We learned that from the second law of thermodynamics, the change of the entropy of the universe must be positive. And from the derived equation above, we know that the change of the Gibbs free energy of the system equal to negative temperature times the entropy change of the universe. If this entropy change of the universe is positive, multiplied by the positive temperature in absolute Kelvin, multiplied by negative, you are going to end up having the sign of the change of Gibbs free energy to be negative for spontaneous process. So therefore, for a spontaneous process, the entropy change of the universe must increase, but the Gibbs free energy change of the system must decrease. My expectation for you on this page is you will need to know the relationship between delta G, enthalpy, and entropy change for the system. You also need to know the relationship between delta G and entropy change for the universe, but you do not need to know how to derive these. Because of these belong to the system, therefore we can omit subscript system for all of these thermodynamic terms. And here is the summary of the spontaneity versus the sign of the thermodynamics properties. For a spontaneous process, entropy change of the universe must be positive, whereas the change of Gibbs free energy have to be negative. So for a non-spontaneous process, the change of the entropy of the universe must be negative, whereas the change of Gibbs free energy must be positive. And when the entropy change of the universe equal to zero, Gibbs free energy will also equal to zero as well. And at this point of the reaction is to indicate that the reaction is already at equilibrium. The reaction is spontaneous in both directions. Gift free energies is also called chemical potential. Chemical systems tend to go toward lower gift free energy or lower chemical potential. For example, if the system starts with high concentration of the reactant, you are going to end up with negative value, and this indicates that it's going to be spontaneous in the forward direction. It's going to be spontaneous up until when it reaches the equilibrium where the delta G equal to 0, right? That would be the minimum. Whereas if you start the reaction at the point where you have a lot more of the product, then this reaction would have delta G would be a positive value, which indicates that it's non-spontaneous in the forward direction, but it is spontaneous in the reverse direction. So the reaction would shift until it's reached equilibrium where delta G is equal to 0. And at equilibrium, this is the point where the chemical potential is at the lowest. At the equilibrium point, the reaction proceeds in both directions at equal rates. We call the process where delta G is less than 0 exergonic, and this indicates spontaneous process in the forward direction. And we call when delta G is greater than 0 endergonic, and this indicates that this process is non-spontaneous in the forward direction or spontaneous in the reverse direction. And we call that when delta G is equal to 0, the system is already at equilibrium. Why do we call gift free energy as a free energy? This is because the change of gift free energy is the difference between the energy produced by the process or by the system, which indicate by the change of enthalpy, and the energy loss to the surrounding, which indicate by the negative T delta S. So negative means it's losing, right? So this is losing the energy to the surrounding, and the difference between these two is the energy available to do work or the free energy that is used to do work by the process, which is what we call the change of gift-free energy. For the cellular respiration in our body, when glucose is react with oxygen, it's going to produce carbon dioxide and water, and the energy or the free energy will be released for us to do work. Even though the reaction is produce heat, and that heat is being transferred or lost into the surrounding, but the net or the free energy that is available, that what our body is used to do work, to grow cell, to repair cell, for example. Next, we are going to apply the gift free energy change into how to predict spontaneity of the process. Let's take a look at example 1. Example 1, we are looking at the chemical luminescence in glowing sticks. In these glowing sticks, the oxalic phthalate ester will react with hydrogen peroxide, and many steps occur. Eventually, it will produce phenol, carbon dioxide, and eventually will release light. That's why we observe it as it's glowing in the dark. And if you observe here in the glowing sticks, you will see that in glowing stick, there would be liquid. This liquid contains oxalic phthalate ester, and in this small little vial in there, or the glass tube, in this one it will contain the hydrogen peroxide. When you crack the glow stick, it will release hydrogen peroxide to react with the ester species, and eventually the light will be emitted because of that, right? And you will also see the bubble right here as well that is being formed over time. Those bubbles are the bubble of carbon dioxide that is produced. And in this problem, it asks us to determine the size of the change of enthalpy for the system, the change of the entropy for the system, and the change of gift free energy for the system. Again, sometimes of these word system will be omitted because of this refer to the system. The size of the enthalpy change of the system is depend on whether the reaction is endothermic or exothermic. This reaction emits light, which is another form of heat. Therefore, the reaction is exothermic. So the size of the delta H would be negative. Recall from the previous chapter section, the size of entropy change of the system can be determined from the phase change of the reaction. In this case, you see that the reaction go from the aqueous into producing gas from 0 mole of gas to 1 mole of gas. Therefore, the system spread out because gas is more dispersed than the aqueous. Therefore, the entropy of the system will increase. The sign of entropy change of the system will be positive. And for the delta G, we know that the change of gift free energy is equal to the change of enthalpy minus T times the change of entropy. If you put in the negative side of the change of enthalpy and positive side of the change of entropy, eventually you will get that the overall change of the gift free energy will be negative, because you have negative add to a negative value, the overall therefore would be a negative. And the negative delta G's indicate that this process is spontaneous in the forward direction. Again, to emphasize the reason why this whole term is a negative term, because the temperature that we are using have to be an absolute temperature, which means that the lowest value of the T would be just 0. It cannot be a negative value. The T or the temperature have to always be a positive value. If you have a positive temperature multiplied by positive, that value would be positive, but the positive value multiplied by negative, the overall would be negative. And you have negative add to another negative, the overall delta G would then equal to a negative value. Similar to the fact that if you have a negative 5 add to a negative 5, then eventually your overall would be a negative value of 10, for example. And similar to this as well, negative 5 minus 5 is the same as negative 5 add to negative 5. Is going to give you the same answer. Therefore, in this case, if you have a negative is going to be similar to negative add to a negative. Therefore, the overall would be negative. I would like you to pause video to complete example 2 on your own. When you finish it, then resume the video again to check your answer against the answer key. Example 2, we have the process of oxygen convert into ozone, and we are going to take a look at the sign for this reaction. First, let's take a look at the sign of enthalpy. The sign of enthalpy change can be determined from whether the reaction is exothermic or endothermic. And this reaction is already given to us that the process is endothermic. Therefore, delta H or enthalpy change for the system would be positive. And for the entropy of the system, we are going to determine from the physical state of the reaction. We see that the reaction going from 3 mole of gas to 2 mole of gas. Therefore, the entropy of the system is decreased because going from more mole to less mole. Therefore, in this case, delta S would be negative because it's become less dispersed. So in order to find out delta G, we are going to set up the same equation again. Delta G equal to delta H minus T delta S. Add into those sign, and you will be able to get the delta G to be overall a positive value. The positive delta G tells us that this reaction is non-spontaneous in the forward direction. And again, the reason why the overall delta G is positive, because if you multiply negative value of the entropy change to a negative sign in front of temperature, this term right here would be positive. When you add positive to positive, the overall then would be a positive value. Similar to if you have positive 5 add to a positive 5, then the overall will be a positive value. Because example 1 is spontaneous in the forward direction, and because delta G is negative, so this is an example of exergonic reaction. And for example 2, because delta G is positive and the reaction is non-spontaneous, so this is an example of endergonic reaction. In the previous page, we look at how to qualitatively predict the sign of the change of gift-free energy. In this section, we are going to look at how to calculate the gift-free energy using the standard enthalpy and entropy changes. In Chem 122, we learned that the standard enthalpy change of formation is the heat that involved with forming 1 mole of a substance from its element at their standard state. And the enthalpy for the reaction is equal to the summation of the enthalpy change of the product minus the summation of the enthalpy change for the reactant, where n represents the coefficient in front of each product and reactant. And to calculate for the change of entropy for the reaction, we can do the similar fashion here, where you will need to do the summation of the entropy of the product minus the summation of the entropy for the reactant. And if you know the value of the entropy change for the reaction and enthalpy change for the reaction, then you can plug into the equation for the change of Gibbs free energy, which is equal to delta H minus T delta S. Note that the north side above these thermodynamic function represent the standard state condition at 25 degrees Celsius, 1 atmospheric pressure, and for the concentration is 1 molar concentration. If the thermodynamic function are without the north side, it indicates that those thermodynamic functions are measured not at the standard state conditions. Let's take a look at example 3. Use standard enthalpy and entropy data below to calculate the standard free energy change, which is the delta G here, for the vaporization of water at room temperature 25 degrees Celsius. And what does the compute value for delta G naught say about the spontaneity of this process? Again, example 3 is indicated this is at the standard state because it's asking for the delta G with the north side, and it's asking for the reaction of the vaporization reaction of water. Therefore, first step is you will need to write out the species that are reactant and the species that are product. For vaporization of water is the liquid water that become gas. So the reaction can be written as H2O liquid and then convert to H2O gas. This chemical equation is already balanced. Therefore, we can use this chemical equation to help us determine the change of standard enthalpy for the reaction and the change of the standard entropy for the reaction. The change of standard enthalpy for the reaction can be calculated from the value of the change of standard enthalpy of formation of the product minus the change of the standard enthalpy of formation of the reactant. The product of this will equal to the change of enthalpy of the reaction, and the unit will be in kilojoule per mole. Do the same to figure out the standard entropy change for the reaction. Use the value of the product minus the reactant. Note that in this case I did not incorporate the coefficient because coefficient are 1. Anything times 1 it will equal to itself. Therefore, I just omit the coefficient 1 for these two calculation. The unit for the entropy change for the reaction would be in joule per Kelvin per mole according to given unit here. Note that the unit for the enthalpy change and the unit of the entropy change are not the same. For the enthalpy, the unit is in kilojoule, and for the entropy, the unit is in joule. Therefore, you will need to look at what is the unit that the problem asks. In this case, the problem doesn't specify the unit for delta G. Therefore, you can either change from kilojoule to joule or changing from joule to kilojoule. I'm going to go ahead changing from joule to kilojoule in this case. Changing from joule to kilojoule, you are going to divide this by 1000 to get a smaller value because kilo is a bigger unit. So the number that go with the kilo would be the smaller number. And the value will come out to be 0.1188 kilojoule per Kelvin per mole. Next, calculate for delta G, which is equal to delta H minus temperature times delta S. You will need to make sure that you convert the temperature in Kelvin because the unit of the entropy contains Kelvin as the temperature unit. By adding 273 to the 25 degrees Celsius, you're going to get the Kelvin as 298 Kelvin. And if you look at the unit here, you will see that the Kelvin will cancel out with Kelvin. Therefore, you will see that you are going to end up having kilojoule per mole minus kilojoule per mole. Therefore, the final unit for delta G would be in kilojoule per mole. And because the delta G value come out to be a positive delta G, therefore, in this case, the reaction at this standard state condition, the reaction would be non-spontaneous in the forward direction, which means that at 25 degrees Celsius, the water will not vaporize into gas at the standard state condition. I would like you to pause the video and complete example 4. When you finish, resume the video again and check your answer against my solution. This reaction is already balanced and the coefficient would be 1 to 1 to 1. To find out the enthalpy change for the reaction, then you use the summation of the enthalpy of formation for the product, right? Add together minus the reactant, and you are going to get this answer in kilojoule per mole. For the entropy change for the reaction, then do the same thing, right? You are going to use product summation minus the reactant. You are going to get this value in joule per mole per Kelvin. Then convert this into kilojoule per mole per Kelvin by dividing this number by 1000. Then because these two units are the same, then you can plug both of the enthalpy and entropy change into the delta G equation. And again, don't forget to convert the temperature into Kelvin, so that way in this case, the Kelvin can cancel out and you will have the final answer in the unit of kilojoule per mole. The positive delta G again tell us that this reaction is non-spontaneous in the forward direction. At this condition, the C2H6 will not spontaneously convert into the product. For example 5, the delta H of the reaction and the delta S for the reaction are already given to us. Therefore, in this case, you don't need to set up to find out the enthalpy and entropy change for the reaction again. You can just use these two values to plug into the equation for the delta G. But you will need to make sure that the temperature have to be in Kelvin, and also you need to make sure that the unit for the entropy have to be the same as the unit of the enthalpy. And since the since the example doesn't specify the unit for the Gibbs free energy, therefore in this case you can either change it to kilojoule or change from kilojoule to joule. Either one should be just fine. And if you do the unit cancellation, you will see that Kelvin will cancel out again. Therefore, in this case, the unit for delta G would be in kilojoule. Because delta G is a negative value, therefore this process is spontaneous in the forward direction at this condition. The unit between kilojoule per mole and kilojoule, they are pretty much the same when we talk about the Gibbs free energy or entropy or the standard enthalpy for the reaction, because the per mole is referred to per mole of the reaction. It means that per 1 mole of this reaction, this is how much the free energy that involved. And same thing for this, right? So kilojoule, or it can be kilojoule per mole as well. It would refer to kilojoule per mole of this reaction here. Another thing that I would like to point out is the amount of energy involved here, because example 3 is a non-spontaneous in the forward direction, which means that if you want the reaction to go forward, you will need to input this much energy in order to force the reaction to go forward. Same thing for example 4 as well. This reaction is non-spontaneous in the forward direction, but if you want to force this reaction to go forward, then this much of energy will need to be applied for the process. Now, on the other hand, for example 5, the negative delta G tell us that this reaction is spontaneous, and as this reaction is proceed spontaneously in the forward direction, it's going to give off this much amount of energy. In conclusion, the type of problem that you will see in terms of calculating delta G, you will see that you can find out delta G from calculate each enthalpy change and entropy change individually, and then use them in the delta G equation. Or sometimes the problem is already giving you the enthalpy and entropy change for the reaction, and then you just have to put those into the delta G equation to find out the value of delta G and also to predict spontaneity of the reaction as well. Next, we are going to take a look at how to calculate the change of standard Gibbs free energy using the standard free energies of formation. The standard free energy of formation, or delta G naught F, is the change in free energy of formation when 1 mole of pure compound forms from its constituent elements in their standard state. The standard free energy of formation is similar to the standard enthalpy of formation, As I mentioned earlier, the standard enthalpy of formation is the change in heat of formation when 1 mole of pure compound forms from its constituent elements in their standard state. We cannot determine the absolute value for both delta HF and delta GF. We need to find the reference for that. And the reference value that we are going to determine is going to base off the value of the pure element. We are going to set the pure element equal to 0 for both delta GF and also delta H as well in order to determine the relative value of delta H and delta G. For example, aluminum element in its standard state would be in solid. So the standard enthalpy change of formation and the standard gift free energy change of formation for aluminum, which is the pure element in its standard state, would be set as reference at 0. And any other compound that contain aluminum, just know that this value right here would be the relative value that is measured based off the reference value of the aluminum pure element in its standard state. However, in the previous chapter section, we mentioned about the standard molar entropy. The reason why the standard molar entropy are not equal to 0 because we measure this at 25 degrees Celsius. The only time when the standard molar entropy equal to 0 would be when the temperature is at 0 Kelvin, according to the third law of thermodynamics that we learned from the previous chapter section. The full list of the standard thermodynamic property can be found in the OER textbook, chapter 17.2, page 137 to 154. And again, because free energy is the state function, which is similar to delta H and delta S, therefore, in this case, in order to find delta G, we care only about the state of the product and the state of the reactant. We don't care how it's reached from reactant to product, but we care only the difference in each of these two states. So we can calculate delta G for the reaction would equal to the summation of the delta G formation of the products minus the summation of the delta G formation of the reactant. N is represent the coefficient in front of each species. For example, in this case, if the coefficient of the product is C, then you need to multiply C by the standard gift free energy formation of C and make sure that you sum all of the product together and subtract from the summation from the reactant. For example, if you want to calculate the change of the gift free energy for the reaction from the standard gift free energy of formation, then you are going to use this column here that involved with the standard delta G formation. And if you're looking at example 6, you will see that the reactant would be the nitrogen and the hydrogen, and the product would be the ammonia. Therefore, the standard change of gift free energy for this reaction would equal to the summation of the product minus the summation of the reactant. Don't forget to include the coefficient as well. And the unit for this would be in kilojoule per mole as is given on the table. The negative value of delta G tells us that this reaction is spontaneous in the forward direction. When this process proceeds spontaneously in the forward direction, it would produce this much of free energy. Let's pause the video now and complete example 7. Resume the video again when you finish it. For problem number 7, you need to be able to differentiate between which side of the equation is reactant and which side is the product. And again, do the same thing. We are going to use the standard gift free energy of the formation to help us calculate the standard gift free energy of the reaction that we have here. Again, so the product we have here are carbon dioxide and water. So therefore, I'm going to highlight the carbon dioxide value and also water value as well. Note that water value are given two value, and these two different by the state, right? Physical state are different, and you will see that the value will be different as well. Therefore, make sure that you use the correct value. And water that is given on this equation is in gas state. Therefore, I'm going to choose this value right here. Same thing for the reactant as well. The value for the methanol, there are two values. One is liquid and one is gas. but the given problem gives us in liquid state. Therefore, I'm going to choose the methanol in the liquid state here. And then the value of oxygen, again, the reason why oxygen is 0 because oxygen is the element in its standard state, which is O2 gas. Therefore, the value would be set at 0 for as a reference here. So plug it in. For the summation of the product, you are going to use 2 from the coefficient, multiplied by the value of the carbon dioxide, add to 4 from water coefficient, multiplied by the value of water gas, right? Minus the summation of the reactant. The reactant has the coefficient of 2 for the methanol, multiplied by the value of the methanol that is given in liquid phase. Add to 3 from the coefficient, and 0 is the value from oxygen. Do this math, you are going to get negative 1369.9 kilojoule per mole. Again, the unit would be in kilojoule per mole here. Note that these calculations are based off addition and subtraction. Therefore, the significant figure rule would go off the fewest decimal place in this case. The value of the delta G come out to be a negative value. Therefore, this reaction is spontaneous in the forward direction. Next, we are going to learn how to calculate standard gift-free energy of the reaction by using Hess's law. Hess's law is when you manipulate given equations and given delta G in stepwise reaction to obtain the desired equation and the desired delta G. Hess's law works based on the fact that the delta H, delta G, and also delta S are all state functions. They depend only the final and the initial state. They do not rely on the path taken. Therefore, in this case, doesn't matter what involved in the stepwise reaction. All we need is the final and also the initial state, and we can calculate the value from just that. Therefore, Hess's law can be used not only with the delta G for the reaction, but it also can be used for the delta H and also delta S for the reaction as well, as long as you know the stepwise reaction and also given value for each of those thermodynamics terms. But in this chapter section, we are going to only focus on how to calculate the delta G from the Hess's law. First, let's take a look at how changing equation would affect the value of the delta G. When you have the reaction A plus 2B convert to C, if the change of the gift-free energy for this reaction is 5 kilojoule per mole, then if you multiply this equation by a factor, you will also need to multiply the value of delta G by the same factor as well. For example, if you multiply by a factor of 2, then the gift-free energy will have to multiply by a factor of 2 from the original equation as well. And if you have an equation, let's say the same equation that we see earlier, A plus 2B to C and the delta T equal to 5 kilojoule per mole, when you reverse the reaction, the value of the delta T will be, the sign of the delta T would be changed into the opposite side. For example, if the forward direction is positive, then the reverse process would be negative. This is similar to what we mentioned earlier. If the forward reaction is non-spontaneous, then the reverse direction would be spontaneous. Therefore, in this case, when you flip the equation, you also need to flip the sign of the value of the delta T as well. And when the reaction are combined, you will also need to combine the delta T value. For example, if A plus 2B go to C is combined with C go to 2D, then when you combine and cancel the common species, in this case would be C, then you will also need to add all the delta T involved when you combine the equations. Let's take a look at example 8. Example 8 is an example of Hess's law because there are several equations given in and asking you to find out the delta T for a specific reaction. The tip to Hess's law is that you will need to look at one species at a time. If the species can be found in more than one equation, you will need to skip that species because it's more complicated to deal with. You will need to look at one species that involved with only one equation. So if you look at the reaction that is desired is the 3C plus 4H2 and becomes C3H8, I'm going to square 3C. And as you see, the only carbon that found is in equation 2. And in order to make equation 2 to be the same as the desired equation, we'll need to multiply this whole equation by 3. The result of this would be 3C plus 3 oxygen go to 3 carbon dioxide, and the delta T value would be 3 times of equation 2. Next, take a look at hydrogen. I'm going to highlight this with the green color. You will see that hydrogen can be found in equation 3. Equation 3, however, has only 2 hydrogen. Therefore, in this case, we will need to multiply the whole equation by 2 in order to make the coefficient of hydrogen to be the same as the desired reaction. The product of this would be 4 hydrogen plus 2 oxygen become 4 water, and you will need to multiply the equation 3 delta G by 2 as well. And the last species in the equation is C3H8 or propane gas here. As you see, the propane in the desired equation is on the product side. However, the given equation, propane is in the reactant side. Therefore, in this case, you will need to flip the equation. So you need to flip the equation. When you flip the equation, you will also need to change the delta T to be the opposite sign. In this case, would be a positive sign of the delta G. When you flip equation 1, you will get 3 carbon dioxide plus 4 water become 1 propane gas and plus 5 oxygen gas, and the delta T value from equation 1 will be flipped into a positive value of 2074 kilojoule. Next, you will need to combine these 3 equations that we just manipulate. You will need to cancel the common species in both sides of the equation. In this case, we see that 3 carbon dioxide can be found in both sides of the arrow, so I can cancel that. Same thing for 4 water as well can be found on both sides of the arrow. And you will see that if you combine the reactant side, you're going to end up with the 5 mole of oxygen. And you see that there are 5 mole of oxygen here as well. Therefore, you can cancel those two. In this case, the final equation would be 3 carbon plus 4 hydrogen and convert into 1 propane molecule. When you add off these equations together for the delta G, all you have to do is just add off them together. Make sure that you check your answer by compare the overall equation that you manipulate to the desired equation. These two must be the same. And as you see, this equation right here is the same as this equation. Therefore, this would be the valid value of the delta G. Because the overall delta G comes out to be a negative value, therefore this reaction right here is going to be spontaneous in the forward direction. Let's pause the video to practice example 9. When you finish, resume the video to check your answer against my solution. Example 9 is an example of Hess's law because there are several equations given asking you to find out delta G of the desired equation. In this case, I'm going to look at one species at a time, and I'm going to avoid the species that appear in more than one equations. So I'm going to take a look at N2O. N2O appear in equation 3. And as you see, the desired equations has only 1 mole of N2O. Therefore, in this case, I need to multiply this whole equation by 1.5 in order to make the coefficient to be just 1. If you do this, you are going to get the equation equal to N2O convert to N2 plus half of oxygen, and the delta G will be half of what is given. Next, I'm going to take a look at NO2. NO2 can be found in equation number 1. In equation number 1, you will see that the NO2 is in the product side, but our desired reaction is in the reactant side. Therefore, in this case, you will need to flip the equation. Not only that, you will see that the desired reaction has only one coefficient, but we have two coefficient in the equation 1. Therefore, in this case, you're not only just gonna flip, but you also need to multiply by 1/2 as well, or divide by 2. Therefore, the reaction after you flip and divide by 2, you are going to get NO2 convert to NO plus half of oxygen. And when you flip an equation, the delta G will be positive, and the value would be half of that because we divide everything by 2. The only species that we have not looked at is the NO, or nitrogen monoxide. The reason why I don't start with this species because if you look at the given equations, the nitrogen monoxide appear in more than one equation. That's why I did not start with that to avoid the complication later. And in this case, you will see that the NO that we have, the only equation that we have not used yet is the second equation, and we already used the first one. Therefore, I'm not going to reuse the first equation again because I already used it, I already manipulated. I'm just going to have to deal with the second equation. The NO that is given for the desired reaction is 3 nitrogen monoxide. You already manipulate the first equation that contain nitrogen monoxide, which already contain one of the 3 of the nitrogen monoxide that is wanted in the desired reaction. In this case, you will see that this one NO right here need to add to this 2 NO in order to combine to become 3 nitrogen monoxide. Therefore, in this case, you don't need to do anything for equation number 2 because you will need that 2 nitrogen monoxide. So in this case, we keep it the same. We're not going to do anything. Therefore, the equation would be exactly identical to equation number 2, which is nitrogen react with oxygen to become 2 nitrogen monoxide, and the delta G value, since we did not manipulate anything, is going to be identical to equation number 2. Since we already use all of the equation that's given, the next thing that we need to do is we will need to combine all the reactant sites separate by the arrow and combine all the products together. And if you do that, you will need to also cancel the species that appear on both sides of equation as well. In this case, the species that appear on both sides of equation would be nitrogen, right? Because it's on one side of the arrow and it's also appear on the other side too. And if you look at oxygen, half of oxygen add to another half of oxygen in the product side would equal to 1 oxygen, which is the same as 1 oxygen on the reactant side. Therefore, you can cancel this as well. And if you combine these together, you are going to get N2O plus NO2. And that is going to become 2 nitrogen monoxide add to another 1 nitrogen monoxide. So total would be 3 nitrogen monoxide. And if you check this equation with the given equation, you will see that they both are identical. Therefore, in this case, the delta G of this reaction can come from the combination of all of these delta G. So if you add all of these up together, you're going to get delta G equal to 107.1 kilojoule. And the positive delta G tell us that this reaction is non-spontaneous in the forward direction.